Thank you everyone for being here. This is the Revolution Cancer August 27th, 2022 International Molecular Tumor Board. Today we're going to really focus on SMARC4 and Mtap. I hope that you'll learn a tremendous amount today. We're going to have some really nice cases to present. I have my co-host with me as always. So I have Ramu Subramanian, Silimbaris and Maskamani. We've got Ali Ukar. Ali Ukar, by the way, has a tremendous company in Michigan where he helps individuals at home have access to healthcare. Please look him up. It's called Healthcare Solutions USA. It's pretty remarkable. These are our disclosures. Please know that we are talking solely on our own behalf. What we say today does not reflect any of the companies that we are affiliated with. So today we're going to have a very unique talk. We're going to talk about the GSK pipeline. We're going to have an overview, SMARC4. We're going to talk about 2 SMARC4 cases. We're going to have concluding remarks. So as you know, we have a GSK pipeline every time we talk. We've talked about several pipelines in the past. We did Daiichi Sankyo's pipeline. We did Revolution Medicines pipeline. We did PMB Pharma. Today we're going to talk about GSK. So I think GSK has an interesting pipeline. We're going to go through their molecules really fast. So Dr. Subramanian will talk about this too. But their first drug we're going to talk about is called momelotinib. This is a JAK1/2 inhibitor, also inhibits ACVR1 and ALK2. This drug was actually the reason they purchased Sierra Oncology. They just recently purchased Sierra Oncology to get this drug. This drug is being used in primary myelofibrosis. The data they have is remarkably promising. It's already been submitted to the FDA for approval, and I expect this drug to get approved. The key study was a study that basically looked at 195 patients that were randomized 2-to-1 against danazol after patients had already had a JAK2 inhibitor. So that's the unique facet of this trial. And what was remarkable is they had a very nice overall survival benefit. It has a ratio of 0.73. They saw very good benefits with the spleen, like we see with all the other JAK2 inhibitors. They actually saw a nice transfusion independence population. Roughly around 25 to 30% of patients did not require transfusion after 6 months on the drug, or basically in the 6 months they were on the drug. And so I think this drug is going to get approved. It will be interesting to see where it finds a place in PMF, right? Because we already have ruxolitinib, we already have fedratinib, and we already have pacritinib. Pacritinib really used for platelets less than 50,000. That's how they got into the field. That's their niche, which is actually pretty impressive. But it will be interesting to see what happens here. When you look at PMF, the 2 drugs I'm particularly interested are pelabresib, which is a BET inhibitor. I also like navitoclax in this particular field. And so it'll be very interesting to see what happens. I think for GSK, they're going to have a niche here. They're going to make some money off this drug. I think what will be interesting is to see what happens with the pelabresib ruxolitinib data. They're going into phase 3 now. If that trial is positive, I think that's going to be a little difficult for momelotinib. They might just come in after that, but I do think it's going to create a little bit of havoc in the field. And actually, it's really nice. I hope that that trial is positive. We need different drugs in this discipline. The next drug they have is belantamab. This is a good drug. It was the first BCMA targeting agent that was approved in myeloma. Now we have Abecma and Carvykti, and soon we will have teclistamab. You can see the trials that they're doing. They're trying to move it up. So this was initially approved in later lines. Now they're in first line with BRD. Now this is a very interesting trial. I think this is really quite nice for them. If they can get into that first line setting, they will have a niche as far as BCMA targeting agents are concerned. I think they'll do very well. I would have liked to have seen them do a VRD plus DARA plus belantamab trial, but I do think that that's a very smart trial for them because they're going to have a lot of pressure from Abecma, which is now moving into second line, and from teclistamab, which I do think will get approved later. It's already been submitted to the European Medical Agency and actually can already be used there. And so I do think belantamab is a good drug. I do think they're going to face a lot of pressure. And I think they would smart of them to try to go into first line to try and preempt any moves from their competitors. I do think teclistamab is going to be a very significant competitor for them. Niraparib is a good drug. We all know it as a PARP inhibitor. There are many PARP inhibitors out there, right? So we've got olaparib and talazoparib and veliparib, and so we have various, and rucaparib. But when you look at niraparib, I think it has a very nice niche in ovarian cancer. Now they're in the maintenance setting, irrespective of HRD. The problem there is they just had a warning letter they sent out saying that patients in that setting might actually have a lower overall survival if they're HRD, but not BRCA1 or 2. So that was very interesting to see niraparib a little bit under fire in that setting. But where they had some phenomenal data recently is what I'm depicting here. So what you can see here actually is a neoadjuvant trial they just did in patients with breast cancer that's HER2 negative, that's locally advanced. And what they did is they basically gave patients single agent niraparib, single agent. And they looked at patients who were treated with this to see if they could achieve a pathologic CR with single agent niraparib. And as you can see, these individuals had a tremendous response to niraparib. In fact, 40% of patients with single agent niraparib actually had a pathologic CR. And that's pretty remarkable. So I do think that that's a really interesting trial. Look for niraparib in the neoadjuvant setting. I think they're going to find some footing there. Dostarlimab is a great drug, initially approved in endometrial cancer and then approved for all patients with MSI-high disease. But they have obviously a lot of competition. There's a lot of PD-1, PD-L1 inhibitors out there with Keytruda and Opdivo and Tecentriq and cemiplimab and avelumab and durvalumab and atezolizumab. And so, sorry, I already said atezolizumab and yeah, dostarlimab. So they have a lot of competitors and many people in trial right now. So they're under fire, but they had a really nice data in endometrial and in MSI-high. And you can actually look at them in the New York Times, that article that was published with MMR deficient patients or patients with mismatch repair deficiency. You could see that those patients all achieved a complete CR or basically a pathologic CR, sorry, complete CR. They didn't go to surgery, but they all 18 patients had a CR and did not require surgery, chemotherapy, or radiation for locally advanced rectal cancer. 18 patients in that trial at MSK. It was really interesting data and excellent. The next drug we're going to talk about is an NY-ESO-1 CAR T sort of drug, and I actually don't have a whole lot to say there. I think it's great. It's a new target. It's a new CAR T. You know, it's a little bit of a black box. We'll see what happens there. It's being used in synovial sarcoma and myxoid round cell tumors. Then there's cobolimab, and I'm actually going to let Ram talk about this, but this is a TIM-3 inhibitor, basically immune checkpoint used in non-small cell lung cancer. Ram, thoughts on this?
Right. So before I talk about a full disclosure on dostarlimab in the trial that led to its approval in non-small cell lung cancer, I was the PI, and so I was a senior author as well on that paper. So I have some vested interest in seeing dostarlimab being talked about. So, you know, as you said, Bassem, dostarlimab is one more PD-1 inhibitor, which is a crowded field, particularly in non-small cell lung cancer. In the rectal cancer, data that was had a lot of publicity, particularly in the New York Times, that speaks to how we select patients. You know, it was a highly selected population, small study, and we see CRs, patients not having to go through surgery, and that really talks about biomarker discovery. But in non-small cell lung cancer, we're still struggling to find the right biomarker to identify patients that respond with a significant magnitude and depth of response. We do have some, like PD-L1 expression. And particularly in this crowded field, either you have to have a niche population where you identify who's going to respond very well, or you combine with another checkpoint inhibitor to improve upon the benefit of your PD-1 inhibitor. And that's what this trial with cobolimab is exploring. And there have been phase 1 studies that have shown activity and safety. This is an ongoing study in second-line non-small cell lung cancer. Obviously, we're still waiting on that data, but toxicity is a concern because when you combine 2 checkpoint inhibitors, there is that concern. So that's something to watch out for. And, you have here other checkpoint inhibitors. 2 of them I'd like to point out is one, the LAG-3, which is already, one of them is approved in the treatment of patients with melanoma in combination with nivolumab, which is relatlimab. So there seems to be some promise there for other checkpoint inhibitions drugs. But at the same time, if you look at the TIGIT, which, recently we had the skyscraper studies in lung cancer, small cell, where we did not see any benefit with combining an anti-TIGIT antibody here. So it's a field where there has been, a slight improvement but we're still struggling to find out the right combination of checkpoint inhibitors, to move beyond the current CTLA-4 and the emerging LAG-3. The others with the TIGIT's failure is a little bit concerning, but we're still waiting on the TIM-3 antibody data. So we'll see how that turns out.
Yeah, I think those were great thoughts. I would just say that dostarlimab, the Beijing drug, had some pretty nice phase 1 data, that anti-TIGIT that they have. So the book is out there. Certainly the Roche data was concerning in non-small cell lung cancer and in small cell for TIGIT. In fact, that day, the entire market for all the companies with TIGIT antibodies collapsed a little bit. So that was a little unfortunate. As we talk about LAG-3, like you said, Ram, you've got relatlimab, which I've actually used several times now in melanoma. You know, LAG-3 was a target that really didn't hold properly for a lot of different trials, and then finally found its footing in melanoma. So we'll see. There's a lot of STING agonists that have failed in trials, so I don't know what's going to happen with this particular drug. I think with STING agonists, it really matters which drug you combine it with. There's been a ton of people who've had failures with STING agonists. You can see the other CAR-Ts here. That MAT2A inhibitor, this is a little bit of an old slide. I actually made it roughly a week or two ago. And within the last couple of weeks, GSK actually dropped the option on this drug. Now, the reason I included it is because we're going to talk about Mtap loss, where this particular mechanism is important, but this drug is no longer in GSK's pipeline, which is interesting. That PREG mechanism is unique. I'd like to see what happens there. And a lot of people have CD96 antibodies. We'll see what happens there. So we have this poll that we're going to run now. And the reason I'm running this is because I'd like to see what people have to say. So GSK recently changed their logo, and I'm not going to tell you which logo they currently have. So you just got to tell me which logo you like the most, one or two. Interesting. So it looks like 80% of people like their old logo, which is the first logo they had. So they changed it to the second logo. And so it's interesting to see that. So next poll for us. So let's do that. Stop sharing that. Okay. So what do you think of the GSK pipeline? Do you think, number one, they're in good shape? Do you think so-so, or do you have concerns? Okay, so most people think so-so, which I think is a very nice sort of response, and I think that makes sense. Okay, let's move on. So we talked about the GSK pipeline. I think it's interesting in many ways. I think they have some work to do also. So this is the Insider's Guide to Translational Medicine I've been writing for biopharmatrend.com. The only reason I talk about it is because there's a lot with respect to chromatin, with respect to cell-free DNA, just really chromatin in general that's in there. You can look it up if you want. So today we're going to talk about SMARCA4, so we have to talk about chromatin. And now we don't make any assumptions regarding what people know and what they don't know. You know, sometimes the biology, the biochemistry can be pretty remote in terms of now practicing in the clinic, in terms of when you learned about it. So we're just trying to give people a very fast overview regarding chromatin. So as people know, DNA is complex with histones in the form of chromatin. It's stored as chromatin. The chromatin helps prevent DNA damage, also plays a tremendous role in gene expression and DNA replication. You can see here, this is the DNA. It's affiliated with the histones forming chromatin. Now, we have different types of chromatin. There's euchromatin and heterochromatin. And really, the chromatin matters a lot because when you have loosely packed DNA, that's accessible to the protein machinery that facilitates transcription and the like. When it's stored in heterochromatin, which really is depicted here, that's not accessible to the protein machinery. You get a lack of transcription of various genes. And so this is really important. The cell heavily regulates when you have euchromatin and heterochromatin, and there's a ton of proteins involved in this. So really it's all about the right chromatin at the right time. And you can see, you can look at mitosis, you kind of see what happens during mitosis. During metaphase, you can see what happens with the chromosomes here. During interphase, and you can see when you need to have some semblance of transcription, you have to have the genes be turned on because you need proteins expressed. The chromatin's very loosely packed. So we talk about chromatin, but there's obviously a huge discipline related to epigenetics. And epigenetics is kind of changes that happen to chromatin or the DNA that's irrespective of your typical transcription and the like. And so when you look at epigenetics, we know that this plays a very heavy role in regulating gene expression. It helps alter chromatin structure, and it's implicated in numerous processes. And really the two big epigenomic or epigenetic modifications are DNA methylation and histone modifications. We're going to focus here at the moment, although later on I'm giving a talk on glioblastoma multiforme, and I'll be talking a lot about this. But what happens in the cell is oftentimes histones are acetylated. So we add an acetyl group to the terminal lysine on histones, and that really helps regulate if the chromatin is packed or if it's loose. And so most chromatin modifications occur on histone tails. Most of them involve acetylation, where you get an acetyl group transferred from acetyl coenzyme to histone lysines. It helps loosen chromatin for replication and transcription. As you can see here, you have the histone acetylase transfers an acetyl group to the lysine on the chromatin, which converts it from closed chromatin to relaxed chromatin. So that's really important. You know, the way that chromatin is packed has a huge impact on which genes are expressed. So the cell uses that as a mechanism of regulating gene expression. And that's what we're going to talk about today. So here you can actually see what happens. Here's the acetyl group transferred to the terminal lysine, and that's an acetylated lysine. So there are numerous complexes involved in regulation of chromatin. We call them chromatin remodeling complexes. And essentially these complexes associate with acetylated histones, like we talked about, which is why it's important, because you can kind of see us, the flow that we're basically showing you. We're doing this very nice flow. We just talked about chromatin, and we talked about epigenomics, and we talked about acetylated lysines, and now we talk about CRCs that bind to those acetylated lysines. So just stay with us. We're going through this flow, and we're going to talk about SMARCA4 in a minute. So these chromatin remodeling complexes have 12 to 15 subunits or domains, including a core ATPase domain. And you can see them kind of depicted here. One of the chromatin remodeling complexes is SWI/SNF, and that's what we're going to talk about today. This is actually becoming a very big deal. A lot of researchers are involved in SWI/SNF and doing beautiful work throughout the world. They've really helped us understand this particular CRC. These CRCs alter the arrangement of nucleosomes. So you can kind of see them associated with the nucleosome. They're critically important. They use energy from ATP hydrolysis. So what they do oftentimes is they allow for accessibility of DNA by loosening chromatin structures. And that process requires ATP. And we're going to talk about that extensively today. And there are numerous CRCs. The one we're focused on today is called SWI/SNF. So we talk about SWI/SNF. So SWI/SNF, you're going to see it called a lot of things. You might see it called BAF, which is BRG, BRM associated factor. You might see it called PBAF. Don't worry about this. There are BAF and PBAF complexes. So these SWI/SNF complexes contain 10 to 15 additional subunits for 29 genes. They're tissue specific, site specific in the human body, and only SMARCA2 and SMARCA4 are catalytic ATP dependent helicases. So let's look at this for a minute. Here's your SWI/SNF remodeling complex, right? Here's your BAF, PBAF complex. There are a number of proteins involved here, but the only two proteins here that have catalytic ATP dependent helicase function are SMARCA2 and 4 and SMARCA4, SMARCA2 here. So this is really important. And this CRC is unbelievably critical to regulating numerous cell processes. And it has a big impact on other proteins. So it impacts EZH2, impacts beta-catenin, impacts ROCK1, impacts the estrogen receptor, impacts various EMT transitions, impacts the GLY1, so it has a big impact on sonic hedgehog pathways, and cyclin D1 EF2. And you can see it's involved in remodeling the nucleosome, remodeling chromatin, involved in nucleosome reconfiguration, acetylation, etc. So what happens is this SWI/SNF complex binds the nucleosome to promote accessibility of the DNA region for transcription of target genes. So you can see it here. Now, what happens during this process is you have to have ATP hydrolysis to give the energy required to facilitate this chromatin remodeling. And that happens through SMARCA2 and SMARCA4, which are really depicted here. You can see the ATP hydrolyzed here. Now, what's necessary for the genes to become accessible through SWI/SNF affiliation with chromatin is you have to get ejection of this polycomb repressive complex 2, PRC2. And to eject this repressive complex, which really represses transcription of the target genes, you have to have this ATP hydrolysis, which allows for ejection of PRC2. And that process is completely dependent on SMARCA4, SMARCA2. And so what you can see is if you don't do that, then the target genes are basically repressed. And many of these target genes are DNA repair proteins, right? So during our life, we incur mutations through DNA replication because it's not a perfectly accurate process. There's a lot of infidelity in it. And we need DNA repair proteins to repair those mutations. Otherwise, If you incur a continued number of mutations, you get a certain constellation of mutations. Now you get a cell that can grow in an uncontrolled way, which is really what cancer is. So SWI/SNF is very important because it will associate with the genes that are necessary to produce DNA repair proteins. And it will do that in the context of DNA damage, where it will basically eject PRC2 and allow for those genes to be transcribed and for us to make DNA repair proteins that then assist us to correct those mutations. So what essentially happens, and this is why it's called a switch, is that you basically switch the closed chromatin to the open chromatin through SWI/SNF function. Now, there are many, many Smark family members. So as you can see with SWI/SNF, there's a ton of Smark proteins involved in that process. So Smark just stands for SWI/SNF related, matrix-associated action-dependent regulators of chromatin. There's proteins that are involved in this process. There are many Smark family members, but what's critically important to know is that SMARCA4 has ATP helicase function, or so I should say ATP hydrolysis helicase function. So does SMARCA2. So that's why they're so important. Now you will see SMARCA4 called BRG1, and you will see SMARCA2 called BRM. So now we come to SMARCA4. So SMARCA4 is a SWI/SNF related matrix-associated action-dependent regulator chromatin subfamily A member 4. That's all it is, just a Smark protein that's in that family, and it's SMARCA4. Okay, no big deal. You can see here it has numerous domains. Okay, so that's important. You can see here's that ATPase domain I keep harping on. This is really important. So you can see that basically this gene codes for the ATPase energy engine of SWI/SNF. There are bromo domains, and this is really important because you can use BET inhibitors here. And so the bromo domain is what we really hope that BET inhibitor can essentially address, but the bromo domain is important. So they have a bromo domain, as you can see depicted here. It has helicase ATPase activity like we talked about, and it is a tumor suppressor. So SMARCA4 has lots of functions, right? It's involved in chromatin remodeling. It modulates MYC expression. It modulates the hedgehog pathway. It binds to BRCA1. So this is something that's really important to know. It regulates CD44. It has immune regulation and encodes transcriptional regulation, BRG1. So it's really, really an important protein. And you can see that when it's mutated or when it's deficient, we have significant problems. So the unfortunate thing is that there are over 120 unique SMARCA4 mutations that have been described in the literature. And it is aberrant in 5 to 7% of all tumors. And loss of SMARCA4 leads to overexpression of MYC, which facilitates cell proliferation. It also leads to reduced DNA repair. So as you can see, that would be tumorigenic. That's why it's a tumor suppressor. So SMARCA4, very important SWI/SNF, very important in terms of being a tumor suppressor. So when we talk about SMARCA4 deficient tumors, now this is a unique field. This has only really been described in the last decade. You go talk to most oncologists, they don't know anything about SMARCA4 deficient tumors. That's why we talked about it, right? So I have 2 patients we're presenting today with SMARCA4 deficiency. These are both my patients who gave me permission to present this, but this is a very new field. You don't really get taught this. And so this is pretty cool. What we're talking about today is awesome. So SMARCA4 deficient tumors are little understood, including their pathophysiology, largely because they were just recently described. Here you can see this patient doesn't have any expression of SMARCA4. You can see expression of SMARCA2. You can see Claudin-4 here, and you can see the pan-CK. But the bottom line is they do not have expression of SMARCA4, normally diagnosed, by the way, through immunohistochemistry. So this is arguably the best way to really look at SMARCA4 deficiency nowadays, but you are going to hear it. It's really important to know this. These tumors have a notoriously short life expectancy because they are incredibly aggressive. And so that's something that I think people need to be aware of. There are different subtypes, we'll come to that, and there's no treatment consensus because it's relatively new. So there are 2 big subtypes. There's the SMARCA4 deficient undifferentiated thoracic tumor, DUT, and there's SMARCA4 deficient non-small cell lung cancer. So I'm just going to say that the SMARCA4 deficient thoracic sarcomas are now part of this DUT sort of subtype. So there's really 2 predominant subtypes. You can see the methodology behind it here. So let's ask this question. Have you treated deficient SMARCA4 tumors before? So let me just get to that poll question. So here we go. We'll launch it. Okay, so most people have not. Share these results and we move on. So this is just one slide on the dark SMARCA4 DUT, the undifferentiated tumors, you can see there tend to be very big tumors, oftentimes mediastinal. So this would not be uncommon. There are less than 100 cases reported to date in the literature. They localize mainly in this time, like we talked about. It's normally a young male smoker. And this is striking, right? This 9-to-1 male to female predominance is really striking. It's classically seen in males, classically young patients. It metastasizes to the bone, lymph nodes, adrenal, lung. It's rarely going to metastasize to the brain. So that's something that's important to know. You often have a high TMB. We'll talk about it a little later. Median overall survival is only 5 to 7 months. So that's atrocious, right? So 2-year survival is only 12.5%. So we need to get better here. This is an unmet need. This is a huge, huge deal. You oftentimes see loss of SMARCA4 and SMARCA2, and you have strong expression of SOX2, CD34, SAL4 that differentiates it really from non-small cell lung cancer. So now I'm going to turn it to Ram. We're going to talk about case. Should be really cool. We're going to move on.
Right. So the first case we're talking about is a patient with non-small cell lung cancer. And as you can see on the PET CTs, there is widely metastatic disease. Now in this image here, you can clearly see there is multiple areas of FDG uptake in the chest as well as in the pelvic area. And that's what is reflected here in the coronal slices, where you can see this in the lung, there is this FDG avid tumor, and you can see these bone metastases as well. So this is a tobacco smoking gentleman who's 75 years old and has multiple lesions, not only in the lung, but as well as the lymph nodes, the ribs, and the posterior rib lesion. And we have the biopsy taken from the acetabulum, which showed that it was confirmed that this was non-small cell lung cancer, but it was also a SMARC4 deficient malignant neoplasm. And the PD-L1 testing was done here. And as you can see, that's about 14%. So not high, but not undetectable either. So respectable number. So how does this all figure into how we approach and manage this patient? So obviously, molecular testing is pretty much standard of care in non-small cell lung cancer. And that's the report we're seeing here. As you can see, there is a SMARC4 loss, which is highlighted in this box. And as on our previous discussion, 2 slides before, we talked about that SMARCA4 is associated with a high tumor mutation burden. And that's what we see here, 13 mutations per megabase. And another important but relevant detail is it does not co-occur with what we see as the classic actionable driver alterations. And in this patient, we don't see any of them, BRAF, EGFR, or the whole host of them. And we do see Mtap loss, which we talked about as well. And another point to focus on is the SMARCA4 specific mutation here. As you can see, this is a nonsense mutation. So the transcription ends at this point because it's been truncated. So the likelihood of having a functioning SMARCA4 protein from this nonsense mutation is of low likelihood. And this is not uncommon when it comes to the non-small cell lung cancer with the SMARCA4 mutations. Unlike some of the undifferentiated tumors in the mediastinum we talked about, where there is a complete loss, we can see missense mutations with SMARCA4 in lung cancer, non-small cell type, but they are all associated with, not all, the majority of them are associated with loss of function. There have been some case reports and studies that have suggested some of the SMARCA4 may have a paradoxic sort of a driver alteration type approach instead of the loss of function and the tumor suppressor, loss of tumor suppressor activity that we see in the majority of non-small cell lung cancers with SMARCA4 alterations. So how do we approach in terms of treatment? This is our COMET algorithm, as you can see. And when we look at conventional treatment options, the possibilities are either chemo with IO or IO alone. And in this particular patient, as the PD-L1 expression is less than 50%, the combination of chemotherapy plus immunotherapy is appropriate. And this is the data in the tabular form from the phase 3 studies that have explored chemotherapy platinum doublet in combination with the immune checkpoint inhibitor versus chemotherapy alone. And consistently, we've seen the benefit. That's what this hazards ratio in the last column shows. All of them are less than 1. So this is an appropriate and approved standard of care treatment. But are there other options? You know, one of the questions in the standard of care is, can we use IO alone? And this data that we're seeing in the tabular form again is in patients who had high PD-L1 expression, and this patient did not have that, but he did have a high tumor mutation burden, more than 10 mutations per megabase. So it is a consideration. But again, if the patient has a reasonable performance status, particularly given the difficulty of using TMB as a biomarker in non-small cell lung cancer, which we've previously discussed in some of our previous MTBs, the preference would be obviously going ahead with chemo-IO in the frontline setting. But as we know, you know, how do they respond to this treatment? And generally, the response to conventional treatments are not great. There have been case reports that have shown that IO agents in some patients have phenomenal outcomes, and sometimes even sensitivity to DNA damaging agents like cisplatin. But larger studies have really not shown that to be true. So there may be occasional patients who respond really well. I have had such experience in some of my lung cancer patients. And one of the emerging findings is that the co-mutation status of SMARC4 might play a significant role. We do know that STK11 and KEAP1, these are bad actors that keep popping up in our lung cancer patients. They don't do well. And concomitant KRAS also seems to be a bad actor if you have a SMARC4 mutation. And in terms of operational options, this patient has widely metastatic disease, not something that you jump to with surgery, but given the bone mets, you know, radiation could be an option in the front line along with chemo-IO for this patient. Now, in terms of molecular-based therapies, let's also talk about Mtap loss so that we have a good idea of what are all the options. And I'll let Silambarasan here to talk about the Mtap loss.
Ram. So this is also another interesting case of genomic profiling. So basically, when we do the genomic profiling, it's not only to identify the actionable mutation for the treatment option, in order to understand the entire tumor biology, how the tumor in nature exactly, so that we can have the better clinical decisions while doing the treatment regimen selection. So here we are going to talk about the MTOS loss, which we often see in 13.4% of NSCLC cases. We are seeing the MTOS losses basically. Okay, and you can see over here in the graph, it's very clearly showing in the bottom one that whenever the MTOS loss is there, and you can see 10% loss will be the SMARC4 loss also will be there. So it means that it's quite obvious that it is going hand in hand basically. And also the another one more molecule you will see is that whenever there is a MTOS loss, and also you will get CDKN2A and 2B also go together loss, because all of them are like the first three molecules, all of them are sitting in the one single chromosome, so the amplicon will be entirely lost. So because of this one, right, so what will happen is the methionine salvage pathway, adenosine methionine salvage pathway will get affected mainly. So it is mainly important that when the MTOS is lost, what will happen is it will accumulate its substrate MTA. So indeed, it is inhibiting the molecules of the PRMT5 molecule, so which is against the protein arginine methylate transferase basically. So it will inhibit that molecule, which is very important in order to regulate the histone modifications. Okay, so because of this MTOS loss, the methionine salvage pathway is getting affected, and the MTA is the substrate is getting accumulated. That accumulated substrate, it is going to inhibit this histone protein, which is going to convert, right? So it's all going hand in hand, right? So each and every genomic mutation we are seeing in the tumor, it is connecting with one another, and then thereby it's entirely regulating the so much the signaling pathway. Right. So when we talk about Mtap, right, the Mtap is mainly the key enzyme in the methionine salvage pathway as well as the polyamine metabolism. So it's a first important steps to convert this MTA byproduct. So it's a major byproduct. It will happen. So because of this Mtap loss, what will happen is that it will start to accumulate the MTA molecule. So the MTA molecule is the product which will indeed, it will affect the PRMT. So the PRMT, as I mentioned earlier, it is going to play an important role in the histone modification and all those things. So you can look at the chromosome over here, the chromosome number 9, in the chromosome number 9, P21.3 region. So all these 3 genes of CDK2NA, CDK2B, as well as the Mtap, all of them are sitting closely next to each other. So one of the gene loss, it's also affecting the other gene loss. So it's a kind of a bigger deletion in that particular chromosome region. So all these things plays a very important role in the tumor suppressor, especially in the cell cycle in the bottom level, as well as in the histone modification in the topper level. So all these things going to affect the SMARCA4 efficiency. Right, so that's what earlier Basim also mentioned, that there are contradicting information about the immunotherapy. Right, it's mainly because the Mtap, what will happen is that it is producing the byproduct MTA. That byproduct indeed itself is an immunosuppressive molecule. It will release into the tumor microenvironment. That tumor microenvironment, it will suppress the T cells in infiltration into the tumor, basically. So you know very well the immunotherapy will work when there is the particular amount of T cells, especially the CD4, CD8 T cells should be sufficient enough. Then only the immunotherapy molecules can work majorly. But because of this loss, what will happen that the MT accumulation will keep all these T cells bay from the tumor cells and make them inert, basically. So that's why the immunotherapy efficiency will be so and so on this one. Yeah. So another one more thing, also the same thing here, MTOS loss targeting mainly that the PRMT, and also PRMT overactivity leads to the tumorogenesis, basically, and exploiting now. That's why Basim also mentioned that earlier, the PRMT molecule, inhibiting molecules are coming up in the GSK pipeline, and other so many companies also targeting. So it will be win-win situation for the pharma companies as well as for the patients, that we need to be wait patiently, because the PRMT will be the big boost for in the future to work on, actually. So this is how the entire picture summarized, that very clear, nice picture. It's a summary that is showing that how the MTOS loss will lead to the histone modification, and also how it is going to play important role in the methylation per se, is basically, right? So I will hand over to Basim over here, and then he will take it from there onwards.
Go ahead. Dr. Silambarsan, or Dr. Subramanian. Are you on mute, Ram? You might be on mute.
I am, sorry. Thank you for pointing that out. So we saw about molecular-based therapies, but in the clinic, when we see a patient, we don't have, once we get past the standard of care treatment options, we don't have anything like a molecular-based therapy available as standard of care. We may have to look into more of clinical trials. And how do we target SMARCA4 loss? That becomes the big question. So to understand that, we need to know what is SMARCA4's role, specifically when it comes to lung cancer, particularly its impact on the clinical presentation. When we look for SMARCA4 mutations, it's present in approximately 10% of patients with non-small cell lung cancer. Depending on the literature you see, it could be as low as 5%, or it can be as high as 15%. You can either look for mutations, or you can look by IHC expression, which was done in this particular case. When we looked at the pathology findings, we did notice that this patient had a loss of SMARCA4 expression. And one of the things that we noted, particularly in the mediastinal undifferentiated tumors, there you have SMARCA4 loss. Whereas, as I mentioned previously, you can have also missense mutations in lung cancer with loss of function at the same time. And the clinical presentation is very similar to what Basim discussed in the undifferentiated tumors, which are more sarcomatoid in histology. In non-small cell as well, they are more aggressive, more common in younger males. But of course, in this particular patient, he was over 70 years old. And the consensus is that the loss of SMARCA4 function in lung cancer may lead to genomic instability. And this Kaplan-Meier curve that we're seeing, we're looking at patients with a high versus low expression of SMARCA4, the dotted line at the bottom is patients with low SMARCA4 expression. The top line, the solid line, is patients with high SMARCA4 expression. Clearly, there is a nice separation between these two lines, indicating that SMARCA4 patients do not as well, low expression patients do not do as well as patients with high expression. Now, when we look at the molecular profile, this oncoplot gives us a good idea. Now we can see the SMARCA4 mutations are being pointed out in this block here, which is in blue mostly, which is a truncation mutation, but not all of them. You do have some pink, which is a point mutation. So commonly you have a truncation or deletion, which is complete loss of function, but the missense also points to loss of function. But then look at the other blocks of common drivers like KRAS, EGFR, ALK, MET, ERBB2. They are all mutually exclusive in the majority. So they don't tend to overlap, particularly the classical drivers such as EGFR, ALK, MET, they don't overlap with SMARCA4. There is a small overlap, as you can see here, with KRAS. And this is the population which we talked about, which is associated with poor prognosis. So common KRAS drivers usually are not present, co-occur with them, but when they do occur, it's associated with poor outcomes. And we also talked about the TMB. That's what this top panel reflects. The majority of these tumors with SMARCA4 loss have high TMB, which indicates that they have some genomic instability, which is why you tend to accumulate more mutations in the patients with SMARCA4 loss. And that's what these are pointing at. Once again, these are mutually exclusive, and we can see that the higher tumor mutation burden. And one of the other important aspects, which Basim discussed in detail, that is being exploited as a potential therapeutic vulnerability is that SMARCA4 does not function independent, as an independent protein. It's usually in conjunction with other chromatin remodeling complexes in the sniff complex, and SMARCA2 is a key function, and they basically regulate the chromatin accessibility and gene expression. Now, when SMARCA2, which basically controls this, has difficulty or is not able to do this in an efficient manner, SMARCA4 creates this paralog deficiency where it supports SMARCA2 to complete its function. Now, when SMARCA4 is lost, then SMARCA2 basically has to carry the weight of managing this function, and therefore is vulnerable if targeted because it doesn't have SMARCA4 support. If you can degrade SMARCA2 in a patient with a SMARCA4 loss, clearly, you can have a synthetic lethality and target these tumors. So where are we with that? Several studies have been explored. Some of them are already closed, some are ongoing, which we will talk about as we go forward. But what you can see is a variety of inhibitors are being used to target these SMARCA4 tumors, the BET inhibitors, EZH2, HDAC, as well as trying to target synthetic lethality using, with SMARCA2 paralog deficiency when SMARCA4 is lost, as well as with BRCA mutations, ATR inhibitors are being explored. The interesting aspect of this is that when you see multiple trials targeting a single target, you can also say that we still have a long way to go. Usually, if there is one or two that are far ahead in the development, then we are more successful. This is also something that speaks to our limited ability to target SMARCA4, simply because SMARCA4, in the classic sense, is not a driver alteration, it's a tumor suppressor. And tumor suppressors are notoriously difficult to target, as we know very well from our experience. So here we have our poll question. So for this patient, we have different treatment sequences. One is standard of care chemo IO, or second line, standard of care DOSI, or third line, which is a trial option. The second option is moving the trial up front to the second line, or go for a trial all the way up to the third line. Pick your choice. There we go. I think that speaks to your knowledge of lung cancer and the status of SMARCA4 targeting, because nobody wants to go for a trial, in the third line. You would choose it second or third line because these patients don't do very well with conventional therapies. So if there's a good trial, if it's great, you would even go with it at the front line. Second line is probably where my choice would be, and that's what I would say here, because you may have a good response with IO for these patients, as in some cases we have seen, but given their lack of benefit for most conventional therapies, if they fail that, trying to find a trial in the second line would be very appropriate.
So Ram, I think that was amazing. So what would you do, Ram, exactly? What drugs are you using here?
So I would choose a chemo plus IO combination in the front line, standard of care from like a Keynote 189 regimen. I'd be very reluctant to use immunotherapy alone unless patient is marginal performance status, can't tolerate platinum-based chemo, then you might consider immunotherapy alone. And you'll have a low threshold to find a clinical trial in the second line setting for these folks. Because if they fail the frontline therapy, yes, you have taxotere and ramucirumab option, but we know that overall prognosis is poor. And if they failed frontline chemotherapy very quickly, the likelihood of subsequent benefit from second line chemotherapy is lower. So if there's a good clinical trial, I would go for that. That's why I would choose the second option in that patient. And in clinical trials, as you will be talking about, there are some that look very promising, and I will try to get them on those trials. We'll talk about them when we get there.
Yeah, so like I said, this is my patient. So what I basically did, right, is I radiated that right hip because it was causing a lot of pain. So I immediately radiated that because he was in excruciating pain because this acetabulum been causing a lot of problems. And then did chemo IO, right? But there's a lot of case reports. I just want to make this clear, as you already mentioned. Good case reports showing ipi-nivo had some effect, right? Also case reports showing carbotaxol, Avastin, Tecentriq. And I actually really wanted to use carbotaxol, Avastin, Tecentriq because I like the idea of 4 different methods of attack, right? This is a black box. And whenever I run into a black box, I love attacking it in multiple ways, right? So I can attack it through angiogenesis with Avastin. I can attack it through immunotherapy. I can attack it with 2 different mechanisms in chemo. So I really like that, but he has a lot of neuropathy. So I did not do that. I really like that idea though. And I would have liked to have done that, but I ended up doing chemo IO. I'll just, say that for now, and we'll see what happens. My favorite thing in this patient though, and I'll tell you, is right now I'm trying to get a feel for the biology of the disease, right? So I'm giving him 3 cycles with that radiation I talked about. Then we do another scan. And I swear, if he just has minimal disease, I'm going to radiate all of those spots, right? I'm going to go after every one of them. The spot in the lymph node, ideal if I can get to it, the spot in the lung, and I'm going to try and radiate this. And then stay with, chemo immunotherapy, and then go to some sort of immunotherapy maintenance or chemo immunotherapy maintenance after. But that's
I think radiation is a great idea because given the genome instability and the DNA damage that radiation could cause, that is definitely a consideration for this patient.
Yeah, I think what's really unique about this patient though, right, is he has very minimal tumor burden. So if you just look at this again, we go back, and you already alluded to this, but we'll go back to his scan for a moment, because that's what I think is incredibly interesting about this patient. Even though he's SMARCA4 deficient, even though this is a notoriously aggressive tumor, he only has this one lung spot here, right? He's got this lymph node further up, and he's got this spot in the acetabulum, and that's it. That's all the disease he has, right? So it makes perfect sense in this patient to give him chemo IO, right? Get a feel for the biology of his disease. Is it going to explode through everything where radiation wouldn't make sense? Or is it going to do pretty well, where then you can say, okay, now I've got very minimal disease left. I'm going to go target it and then come in with some sort of maintenance after. And that's what I love doing. That's like my favorite approach, to be honest, in almost all of medicine, to do local regional therapies if I can, come in with a maintenance therapy behind it, and to induce initially. And so that's what I'm going to do with him.
Right.
Yeah.
And the reason why this patient has sort of this low burden disease may not just be serendipity. There may be a very good reason for that. Because of the genomic instability and the high tumor mutation burden, you may have more tumor neoantigens here, which means your immune system is surveilling this tumor better than something with low tumor neoantigens. In that case, those tumors tend to be more sort of localized without like widespread metastasis. So his immune system might be in a good shape, but we don't know whether the agent that will continue to or expand or like enhance the immune system would be the checkpoint inhibitor or your radiation treatment. We don't know. So making sure you try all of these options in our kit makes a ton of sense.
Yeah, I'm with you. So let's talk about this patient, because this is a mind-blowing patient. This is the coolest case of my entire career, which spans over a decade now. This is a ridiculous case. So this is a 66-year-old female patient of mine, stage 4 SMARCA4 deficient non-small cell lung cancer. Has this particular molecular profile. You can see it here, have the SMARCA4 mutation. On pathology, she was SMARCA4 deficient by immunohistochemistry. This patient refused chemo IO, which I wanted to put her on, refused it. Okay, said, look, I want to be left alone. We'll just do a scan in 3 to 4 months. And that's what we did. So she let me do it 4 months later. Okay, she didn't let me do it within 3 months. That's perfectly fine. No changes, nothing in the form of supplements, no changes in terms of drugs, nothing changes. So initially, she had this lymph node in the axilla. She had 2 lymph nodes, multiple lymph nodes in the mediastinum. She had multiple lymph nodes in the hilum, and she had this lesion here. So without treatment, I didn't do anything here. I didn't do anything, literally did nothing. You can see the tumor regressed on its own. This is a notoriously aggressive tumor, but this shows you that cancer does not read textbooks. It does not care what you think should happen. I always tell people this when I'm training fellows, training residents, look, yes, it's important to try and anticipate what's going to happen. And I built an entire article on this. So, I wrote this playing chess article saying, hey, you got to know what the future is going to look like. But no matter what you do, you're not God. And the cancer continues to prove that every single day of our careers, Ram, proving to us we're not God. We don't know what's going to happen. And so here's the deal. So she got better on her own. It's pretty remarkable. It shows the immune system is probably very active here. Ram, I'd like to get your thoughts here.
No, if you treat patients with lung cancer long enough, we all run into 1 or 2 of these patients in our career, which are in some ways career defining and very humbling. As a medical oncologist, we learn from our patients, and that's what we see. And once again, the point I made was the immune system there, maintaining a strong anti-tumor surveillance. And one of the interesting things would be in this patient, if we had the ability to look at the mutations that happened over time for this patient, right? Or the gene alterations that happened. We think, in a very simplistic fashion that cancer is a stepwise accumulation of mutations until it turns into a full-blown cancer, right? So it doesn't always work like that, but some mutations or truncal mutations happen much earlier during tumorigenesis or carcinogenesis. Some happen much later. And this is a hit or a miss. The tumor doesn't get to choose which mutations happen. It happens. But the same mutation that allows it to suddenly turn malignant and become active may also be the same mutation that triggers the immune system. Sometimes we know this when we treat viral infections, viruses that cause high mortality, like, rapidly kills people. Also rapidly, the human or the animal tends to develop an immune response to it. And these tend to die down much quicker than a more sort of indolent, slow spreading disease. And that applies to cancer as well, in my opinion. Of course, this is all hypothesis. This is not very well grounded on science, but there are some indications from science that may be the case. So the same gene alterations that gave it the evolutionary advantage to suddenly explode and grow also was the Achilles heel that probably triggered the immune system, which is why you have this symptomatic presentation with widely metastatic tumor that you identify this patient, and then boom, 3 or 4 months later, you have a complete response without any treatment, right? So the same mutation triggered the immune system, and in 3 months, your immune system woke up, her immune system woke up and said, you're going down.
Yeah, I mean, these patients to me are research gold mine. If you could do multiomics before and after, right? And just look and really analyze the multiomics, there is a tremendous amount of information you could get from a therapeutic perspective in terms of trying to develop new targets. I just think that these patients are a research gold mine, right? But we see this in melanoma, to your point, because it's a highly immunogenic tumor. We see it occasionally in lung cancer, to your point. But I think it's unique. This is SMARCA4 deficient tumor. This is definitely reportable. I could write this up and we will certainly do that. But the bottom line is it's an incredibly unique case. Let's move on. So in terms of unmet needs, right? Obviously, SMARCA4 loss is associated with poor prognosis. It's a pan-cancer marker and possible target. Current standard care options show marginal efficacy. We overall need to get better at understanding SMARCA4 loss, and tumor suppressors are notoriously difficult to target. Ram, thoughts here?
Again, we talked about this. There is a big unmet need in the sense that, yes, we have some patients that respond well. But as I said before, the larger studies that have looked at it, have not borne it out that these patients always consistently respond well to immunotherapy or chemotherapy for that matter. So definitely a lot of work to be done here.
So clinical trials we'd like to see. Now, listen, this is not rocket science, and lots of these are being done in single agent, but I think combination therapy would be really nice here. I'd love to see a phase 1/2 BET inhibitor. Pelabresib is a nice option here, plus an EZH2 inhibitor. I'd like to see it maybe in second line. I think that would be a really good place to put this instead of using Taxotere plus minus ramucirumab, depends on what your preference is. I'd like to see something like that. And so you got tazemetostat, you've got velmetastat. There's a bunch of EZH2 inhibitors out there, and they've also have several BET inhibitors. But I'd like to see something like that, maybe third line. I'd also like to see a phase 1/2 CDK4/6 inhibitor plus the PRMT5 inhibitor. So many of these tumors also have cyclin dependent 2 or cyclin D2 lost. And so it would be nice to see some inhibitor of CDK4/6 with the PRMT5 inhibitor. There's several actually that are available. And that's something you get from this tumor you don't get from others, right? We're talking about PRMT5 inhibitors and all of them that are currently in trial. And it's all of them that they're depicted right here. So you won't really see that. They're being tested in Mtap lost solid tumors. It's really nice. So Ram, do you want to talk about genetic counseling implications?
Right. See, before I get into this, I did want to point out one thing about the trials that you showed on the previous slide. 10 years ago, the same agents, if present, you would have these studies. But the good thing that I think has changed is they're not giving it to every patient with, after they fail the front line. The one good thing that I think we've learned in the last 10 years when it comes to clinical trials, particularly with targeted agents, particularly with these rare alterations, which are tumor suppressors, don't try to hit everybody that's out there with these drugs. Choose your patients. Now, these drugs, whether they'll win, whether they'll, get to phase 3, we don't know. But I think the good thing that's happening here is that they are using biomarkers to select their patients. So even if they don't succeed, our knowledge on how to use these agents and the biology of these tumors will expand, I'm hoping, as these studies or the results from these studies are presented. So genetic counseling implications, in a patient with lung cancer that presents with the SMARK4 variant, these are all somatic variants. So the likelihood of needing a genetic counseling there is low likelihood, but never underestimate, because SMARK4, particularly in germline, can be associated with some significant debilitating syndromes like the rhabdoid tumor predisposition syndrome. These are very difficult diseases to treat. Aggressive rhabdoid tumors right from infancy for these children who don't have a very long lifespan. The other one is a Coffin-Siris syndrome, which is characterized by significant deformities, including microcephaly, hypoplastic nails, and very unique facies. And this rare syndrome, which we see in more adult patients, is the small cell carcinoma of the ovary, hypercalcemic type. And not all of them have SMARK4 deficiency. 40% of them have. And again, you don't have a large case series for these patients. You see case reports here and there. They do seem to respond to systemic treatment with both chemotherapy or immunotherapy for that matter. So if somebody has a SMARK4 in lung cancer, particularly a missense mutation, low likelihood. But if you see a small cell carcinoma of the ovary with hypercalcemic type, you need to be careful. You need to think about genetic counseling. Why genetic counseling? It may not change what you do for your patient there, because they're already dealing with cancer, widely metastatic. It's about their family more. They obviously might have children, they might have siblings, and they could all have potential impact, even their parents. So it's worth making sure that analyzing whether they need genetic counseling or not. If you're not sure, call a genetics counselor. Many times that's what I do. I don't have all of these answers. When you don't have the answer, get help. That's what we need to be doing.
So one sec, I want to show that. Just want to say really quick that these pictures here are actually a patient with small cell carcinoma of the ovary. Completely agree with you. The genetic counselors nowadays are amazing, and this field is changing so fast. I do think that we will be sending patients with SMARK4 deficiency routinely to genetic counseling in the future. I think we just don't know enough right now. I think it's going to happen. But yeah, it's pretty amazing. Ram, close this out.
Sorry. So in conclusion, SMARK4, this is not as well known like EGFR or ALK or RET, but it is an entity that any treating oncologist, not just the oncologist, people on the nursing side, advanced practitioners, pharmacists, anybody that has any connection to a patient with cancer or researchers knowing about these SMARCA4 deficient tumors makes sense because many times they kind of fly under the radar. You know, when you see a molecular testing report, you see SMARCA4, you just forget it. But it does have some implications, as we talked about. You may not have a standard of care therapy to apply, but you can prognosticate for these patients. You have an idea that here we are dealing with a very aggressive tumor, most likely. So we better come up with good treatment options. Like one of the discussions, even with standard of care, like we talked about, was to give chemo IO, and given the oligometastatic nature of the presentation, you know, locally acting therapies like radiation to treat the tumors would make sense. Also, if they do fail your conventional frontline treatment, search for the clinical trials. I think that is going to be very important because these patients, the likelihood that if they don't do well with the frontline therapy, the likelihood that you'll catch up on a second line, I think is small. So finding a good clinical trial would be very important. And in terms of Mtap loss, not all SMARCA4 deficient tumors have Mtap loss, but almost all Mtap loss tumors will have a SMARCA4. So why does it matter? So if you're going to look for clinical trials, knowing if there's a co-occurring Mtap loss could help you narrow down those trials. As you saw, Bassam discussed 2 trials, one of them in SMARCA4 patients, the other one the Mtap loss patient. So make sure, you know, when you look for SMARCA4, you not only prognosticate, you have this high degree of suspicion on how you treat these patients, choose your good standard of care treatments, but co-occurring alterations matter. They matter in prognosis, like we looked at KRAS, STK11, and KEAP1, but Mtap could point you in an entirely different direction in terms of clinical trials. And that leaves a lot of room for creative trial designs, and both are significant areas of unmet need. Hopefully, before I retire, I hope to see some progress in this field. And with that, we conclude. Thank you for being here today. And if there are any questions, I'd be happy to take them, as well as our team.
Okay, well, I think that was amazing. Thank you everyone for your time. We'll be back in 2 weeks. Ram, any final comments? Silan Barson, any final comments?
I'm good.
All from my side is okay.
Thank you, everyone. We finally got this to an hour. We worked really hard to do that. Please take care. We'll see you in 2 weeks. Congrats. Take care, everyone.
We should all pat ourselves on the back for being on time.
Yeah. All right. Have a good one.
Take care, guys. Bye-bye.